Hi there. Welcome to the third in the Campus NetBuilders webinar series. My name is Paul Druce and I'm a Systems Engineering Manager at Arista Networks. This series has been focusing on the cognitive campus network solutions and has covered topics such as architectures, automation, visibility, and secure connectivity in the campus. This webinar within the series will take a look at segmentation in the campus and evaluate the traditional as well as some more modern segmentation techniques available within the Arista campus solutions. I'm joined today by my customer engineering colleagues Tyler Conrad, Murthy Devarakonda, Neha Goyal, and Max Fayezi. Together they are going to go through an overview of segmentation concepts relevant in the campus, dive a little bit deeper into how EVPN, VXLAN, and group segmentation can assist, and take a look at CloudVision and some more campus-related use cases within the product, and round it out with some troubleshooting examples of EVPN in the campus. With that, over to you, Tyler.
Hi, I'm Tyler Conrad with Arista Networks. Today we'll be talking through some of the design goals behind campus segmentation. So when looking at traditional segmentation models, you'll typically see that most of the security enforcement is deployed at the edge of the network. Network operators often create two security zones: internal, or trusted networks, and external, or everything else. Where this falls apart, though, is if an attacker is able to gain a foothold inside the trusted zone. Then they might be able to move laterally inside the network, completely bypassing security controls at the edge. So to help protect against this, we can deploy segmentation inside the network. ACLs, VLANs, VRFs, and firewalls. These, when used together, help form the layers of the networking segmentation model. We can use ACLs to match against traffic crossing the switch, and then permit or deny traffic. VLANs and VRFs are ways to separate out traffic at layer 2 and layer 3, but one thing to note is that VLANs and VRFs also have the ability to be extended through VXLAN. And then firewalls are what provide the deep inspection capabilities, as well as the granular policy application. When it comes to ACLs, you'll see two main types referenced: RACLs and PACLs. The real difference between them is where the ACL is enforced. So RACLs, or router ACLs, they're used on layer 3 interfaces, meaning an SVI or a routed port. These are really only used by packets routed by the system, meaning if you have two hosts that are on the same VLAN communicating with each other, the RACL's not going to process it. To contrast here, PACLs, or port ACLs, can be enabled on individual switch ports and then match traffic coming in on a per port basis. This means you could filter between hosts in the same VLAN segment. Now, VLANs. We can use VLANs to separate out traffic at layer 2. And typically you'll see one IP subnet per VLAN, and then hosts within a VLAN can communicate freely by default. Then there's also the concept of a private VLAN. Private VLAN, or PVLAN for short, allows you to define a pairing between a primary VLAN and one or more secondary VLANs. As an example, say you have an IoT or Internet of Things VLAN, where you know that your devices don't need to communicate with each other, and in fact, you don't want them to communicate with each other. PVLAN isolated could be a good fit here. This makes it so that hosts on the same secondary VLAN cannot communicate with each other, but they can communicate with anything on the primary VLAN, meaning their default gateway. Alternatively, say you're running a manufacturing floor, and you want to use the same IP subnet for the entire floor, but only allow specific groups of devices to communicate with each other. In this case, you could use community PVLAN to create communication islands, where within the same community VLAN, devices can communicate, but between communities, that traffic is blocked. And now VRFs are becoming more and more common in campus environments as well. The biggest driver for using multiple VRFs is often going to be the need for high-speed routed traffic within the VRF, while still keeping that granular segmentation by using a firewall to route between VRFs. In this example, VLAN 10 and 45 can be routed by the switch directly, but in order for any host in VRF internal to reach the DMZ VRF, they have to route to the firewall first. And finally, let's see how this all stacks together. So in this example, we have three different VRFs: green, blue, and red. VLAN 20 and 200 are in VRF blue. If we wanted them to communicate, they could route freely by default. But if we wanted to filter them in some way, we could put a RACL on each of those SVIs to protect them from each other. Now, take a look at VLAN 10 and 30. They're members of different VRFs, VRF green and VRF red. So if they needed to communicate, they would follow their default route to the firewall, which would then verify the policy, route the traffic, and then place it into the destination VRF. The firewall doesn't need to be VRF aware in this case. For all it knows, it just has two layer 3 interfaces. So to wrap up here, we've discussed the typical segmentation building blocks that have been used up to this point as an industry. Now I'll hand over to Murthy, where he'll discuss some recent Arista innovations in this space.
Thank you, Tyler, for covering traditional segmentation methods in your slides. As you can see, traditional segmentation methods are not sufficient when there is a heavy proliferation of IoT devices in the network. Due to limitations of networking stack, these IoT devices require layer 2 adjacency across the entire campus network. Cost of firewalls increases tremendously as the throughput needs increase, and the security needs to be offloaded to the networking to save cost. Enterprise network cannot be static anymore. It needs to be agile to meet the network demands, especially in large enterprises. There is a need of location agnostic connectivity where the end users and the devices roam between buildings and networks. There is a requirement for consistent segmentation across the network. Arista addresses these needs using modern segmentation techniques. In this section of the presentation, I'll be covering how EVP and VXLAN and MSSG, in short for group-based multi-domain segmentation services. Before we discuss on EVP and VXLAN and MSSG, let's review some of the popular Arista campus designs. There are a series of building blocks that enable these designs. First up in the campus is spline. The term spline denotes the flexibility of this layer. Think of it as an aggregation layer that can reside either in campus MDF or even in DC itself, part of a wider fabric. The spline can be a PoE or non-PoE enabled layer that in turn is used to aggregate connectivity to individual campus PoE access pods. The campus pods consist of fixed modular wiring closet access devices that offer PoE connectivity to clients. The campus pods can be deployed with single device for single attached workloads or a pair of devices with multi-chassis link aggregation for active-active or active standby attachment of clients. And finally, campus pods deployed with the two layers of devices for flexible open standard scale-out alternative to stacking. These designs are either layer 2 enabled as depicted on the left-hand side with the campus spline being the delimitation for L2, L3 domain, which is suitable for small and medium-sized enterprises. Alternatively, on the right-hand side, for a highly scalable implementation, we can look towards layer 3 being all the way down to the campus pods. This design is complemented with overlay VXLAN for L2 mobility. This solution is suitable for large enterprises. We will focus on option 2 in this presentation. Let's review in this slide how BGP, EVP, and VXLAN segment the network. I will not dig deep on how VXLAN technology works in this slide, but I will cover some fundamentals. Fundamental building blocks of BGP, EVP, and VXLAN network fabrics are underlay network, which is capable of configuring BGP IPv4 address family, overlay network, which is capable of configuring BGP, EVP, and VXLAN address family and defining the network segments and traffic flow policies. You might have noticed that this architecture inherently isolates the underlying network from the overlay network. It provides the foundation for building elastic, logical networks that span L3 network boundaries. The overlay network pools the network resources and applies the granular network traffic policies. In this architecture, L3 boundaries are isolated to the campus pods and L3 gateways for those L2 boundaries are located on the campus pod switches itself. Typical deployment associates user groups to VLANs and VRFs. Based on the need, these isolated layer 2 segments can be extended to other pods through mapping of VLANs to VNIs, in short for VXLAN network identifiers. Further segmentation can be achieved by isolating the L3 interface into VRFs. You can see that the devices can only communicate with each other devices in their own segment. Through granular network policies or through integration with firewalls, you can allow or disallow traffic flows between these segments. BGP leverages both IPv4 and EVP and VXLAN address families to build the underlay and overlay network. Another advantage in EVP and VXLAN inherently suppresses the ARP broadcast at the pod level. This architecture enables consistent network segmentation across the enterprise networks. Since we are using industry standard protocols, we can easily interoperate with the various other network vendors. It also addresses the adverse impact of learning MAC address through forwarding plane. BGP control plane exchanges the newly learned MAC addresses and routes to all BGP peers and scales better. This slide shows the logical representation of EVPN VXLAN overlay. By using Anycast gateway configuration, hosts in each segment can reach to closest default gateway that is hosted on the campus port switches. As of now, we have segmented end hosts based on their role to a broader segment, right? That is VLAN and VRFs. The historical and simplest form of segmentation are port-based access control lists, VLANs or VXLANs with the routed ACLs, and VRFs to regulate client communications. Of course, the firewalls are used at the network edge for protection from external connections. Traditional methods of segmentation can be cumbersome and demand for scarce resources on the hardware, such as TCAM. These segmentation methods are not sufficient to contain the lateral movement of compromised hosts within the same VLAN IP subnet. Granular segmentation of campus networks requires a different approach, especially with the growth of IoT devices. Fundamentally, security segmentation groups need to be defined independent of network IP constructs. Arista addresses this need through MSSG. In the coming slides, I will present on MSSG. In this slide, let's review briefly on various segmentation options provided by Arista. ACL VLAN-based segmentation is suitable for small campus where NAC software provides the policy control. This solution may impact the availability of scarce resources, hardware resources, that is TCAM. MSS Firewall integrates with firewalls for policy control. This solution is more suited for data center networks. MSSG is a group-based segmentation solution which is suitable for large campuses. Group policies can be static policies configured via CLI or network devices, or can be dynamic through the integration with third-party NACs, in this case ForceCode and Arista CloudVision. MSS Group applies authorization policies to security segment groups rather than interfaces, subnets, or physical ports. IP addresses and or IP subnets are placed into administratively defined security segment groups. Policies are applied to each group that defines both inter- and intra-segment group communication. MSSG does not obsolete the existing segmentation methods. In fact, it can commingle. Please note that MSSG is not modifying the Layer 2 or Layer 3 headers for segmentation. It is leveraging hardware and software capabilities of Arista switches to create segments. Arista switch hardware has built-in ability to create security segments and enforce policies between those segments. As a network administrator, you will configure the segment groups and traffic policies between those segments. There is so much flexibility in defining these segments. A segment is a collection of IP prefixes comprising a single security group with identical reachability properties. As an example, guest IP phone security cameras. The segment name can be anything and is assigned by the network administrator. Policy that defines what other segments a given segment is allowed to communicate, including if it can communicate with other members on the same segment. The switch can be configured in a variety of ways, including Arista standard CLI or eAPI, which is sufficient for few switches. However, for larger deployments, an orchestration layer like CloudVision is recommended. Orchestration layer can receive the policy from policy layer. Currently, we have an integration with the ForceCode NAC. MSSG can be applied both routed and bridge traffic. Configuring MSS group feature broadly consists of the following steps. Define prefix IPv4, IPv6 match list. Define segments using match list. Define policies between segments and enable the feature. This slide briefly discusses the three planes in MSSG implementation. Policy and admin planes where third-party policy servers live. CloudVision resides in the orchestration layer and receives the policy definition from policy plane and pushes the configuration to the enforcement layer, that is a switch layer. Let's review MSSG with a demo. Right? In this example, cameras are not allowed to talk to each other, but they can talk to DVR. Cameras cannot talk to employee devices, but can talk to security admin devices. Security admin devices can talk to all devices. Note that all three device groups can be either in the same IP subnet or in different IP subnets. Definitions of segments can be static through CLI or dynamic through integration with a third-party NAC and CBP. Arista partnered with Forescout in this architecture. We are also actively working with other NAC vendors. In the dynamic policy case, NAC will be posturing the end devices and associate those to a security group, and segmentation configuration as well as a policy will be pushed from that layer to the network devices by Forescout, in this case through CloudVision. This is the demo topology here. In this demo topology, we will demonstrate how we can configure the segments and policies from the Arista CLI. In this example, DVR and cameras are in the same VLAN and IP subnet. Employees and security administrators are on their own VLAN IP subnet respectively. VLAN 10 is for cameras and DVRs, VLAN 20 for security administrators, and VLAN 30 for employees. You see here, like I defined already some segments here for employee and camera. And what I'm going to do is I'm going to go and shut down the router segment security here. I'll apply shutdown on floor number 2 switch as well as floor number 3 switch. Basically, I shut down the policy which is already configured, and then I will show you how I can ping from employee to the cameras, camera to cameras, DVR to camera, and admin to camera segments by using one of the PCs as a camera in this example. Right now, when I show segment security hardware counters, and I don't see any hit because the policy, the router segment security is shut down right now. And I do the same thing on floor number 3 switch also to show the counters. And right now, there are no counter outputs, right? And now what I will do is I'll go to the PC, and that's camera 1 as acting as a PC. In this case, .10 its IP address, and I can ping to .11, which is camera 2, and .12 is the DVR. So I can ping from camera 1 to all those devices. I can also ping to admin group, which is 20.10. And then also I can ping a device in employee segment, which is the 30.10 in this case, right? If I go here, and I say no shutdown, I enable the policy right now, and I would say no shutdown on the CLI. And now I try to do the same thing. I try to ping between the cameras, right? I cannot ping because as I defined in the demo topology, I defined the cameras to cameras cannot talk to each other, right? But I will also try to ping the DVR, and which should be allowed. And I will ping that once this is timed out. Then I'm pinging the DVR, and you see from here I can ping that particular DVR, and I will try to ping the admin device, and I can ping because the policy is defined to allow. But I try to ping an employee device, right? And I am getting dropped because the policy drops the traffic as such, right? And now let's look at the hardware counters. So if you see here, there is a hit count and there's a drop count. Hit count means the policy was hit, and the drop count means when the packets are dropped. And you can see from here, camera to camera traffic was dropped 4 times because we sent 4 pings. It was matched. And the camera to admin, which was allowed because we pinged camera to admin device, as well as camera to DVR, we tried pinging. So our traffic policy is showing here. Right, there are only 2 policies here, policy drop all and policy forward all. We don't have an intermediate between, right? So either you allow the traffic or drop the traffic at this point. And we can also see here from DVR to DVR, DVR to camera is allowed, right? And admin to camera was allowed here too. So you can see, look at the counters and all this. And I issue the same command on floor number 3 switch, and you can see the similar kind of counters where, we allow traffic between DVR to camera and camera to DVR, right? You can see this traffic was not dropped, so you don't see under drop counters. Let's do one interesting thing. Right now, the traffic between camera to camera is dropped, right? But let's move the camera into a DVR segment and see how the traffic is allowed or disallowed from there, right? So let's look at the policy. how we will be doing. We'll simply moving the IP prefix match from camera segment to, and then add that to DVR segment, which is already the policies allowing the traffic between camera and DVR. So let's quickly configure that one on both switches. And here in the match list, I'm removing the prefix match for camera. So I remove no match prefix IPv4, and then I remove my 172.0.10.11/32, and then add this prefix to my DVR segment because the communication between DVR and camera is allowed. So I've moved this prefix to a DVR segment. So I'm in the DVR segment configuration right now, and then I am matching the prefix IPv4 172.0.10.11/32, and I show segment security here, right? You can see that the policy is like how we define the policy, right? DVR to DVR, DVR to cameras is allowed, right? And right now show segmentation policies. Right now, camera is only .10, and then DVR you have 2, right? And 11 and 12. 11 says initially we configured it as a camera, right? And we configure the same thing on floor number 2, switch 2. And remove the matching that IP from the segment camera segment, the 172.0.10.11, and then add that particular prefix to the DVR segment. And the same thing like it shows segment security hardware detail. So you can see that there are 2 IP prefixes under DVR segment right now. So let's try to ping from camera 1 to camera 2, right? In this case, since we moved, .11 is successful. Let's recap the CLI configuration, what we have shown in the demo. First, we defined the match list, which matches the interested IP prefixes. Second, we enabled segmentation, segments, and defined segments in segment membership. Then we created policies. These policies decide whether a traffic flow is allowed or disallowed between those segments. In the last slide, let's quickly recap on MSSG. It is a brownfield-friendly architecture. Enforcement is on Arista switches, but upstream and our downstream switches could be third-party. No proprietary Ethernet data plane is required. It is an end-to-end architecture. Single architecture can be deployed across DC and campus without complex overlays. We support policy controllers from other vendors. Segment membership can be fluid and dynamic. This technology does not tax on the hardware resources such as DCAM. I will pass the ball to my colleague Neha to demonstrate on Cloud Vision capabilities. Thank you.
Thanks, Murthy. In our last NetBuilder session, we covered some parts of Cloud Vision. Let's take that discussion a step further. Today we will talk about telemetry, an example of provisioning of Day 1 and Day 2 BGP VXLAN EVPN deployment, compliance overview, events, metrics dashboards, and topology view. Talking about telemetry, CVP has some inherent advantages over other network management tools. Legacy network visibility approaches are often based on periodic polling mechanisms like SNMP. The updates happen every polling interval, and cycles are wasted repeatedly pulling data that might not have changed, or we could miss an event update. The inflexible MIBs would also limit the actual network state that can be collected. CVP uses a state-based approach. EOS devices are configured to stream device state data over a secure gRPC connection to CVP using Terminator agent that is run on EOS. Streaming makes the updates possible at the very instant a change is made, and a lot of network data can be collected, such as configurations, buffers, counters, flow data, etc. Let us look into Day 1 provisioning of our campus network. This is when we are bringing up a new network and all our devices boot up in ZTP mode. DHCP configuration could be used to point the devices to CVP. This would allow an initial boot config to get the devices in the undefined container, and CVP can manage these devices from there. Right now, my devices are going through a ZTP boot and will soon show up in the undefined container. Network operators can organize devices in logical hierarchies through container views for rapid categorization of devices by role, type, location, or other specification. The switches at the bottom of the tree inherit the configuration and software images associated with the top-level container. Configurations can be broken down into more manageable configurates and are ready for network-wide or group-specific provisioning. For today's demo, we are going to see one of the ways to automate our day one provisioning process. This is an example of integration with the CVP APIs. I'm going to use a script fabricdeployment.py that interacts with these APIs. It sees all the devices in the undefined container and knows their names based on the descriptions. This script makes use of the Fabric Stamp configurate builder and the NetBuilders.yaml as input files, which have been uploaded to CVP. These files can also be hosted somewhere else for CVP to get it from. In this example, the campus leaf and spline containers have been pre-provisioned. A global config common to all devices based on the company policies has been applied to the top-level NetBuilders container. The script moves these devices to appropriate containers and generates the config to build the fabric, which includes point-to-point connectivity, IP addressing, PGP configurations, EMLA configurations, etc. The script also picks any device-specific configurations, example configurations only meant for spline or leaf-specific .1x profile configurations, etc. Here I have two examples, banner config for the spline and the interface profile config with the necessary .1x configuration for the leaves. Here we can see the devices are being moved, configurates are being generated, and tasks have been created, after which the network admin can validate, approve, and push these to the devices. Once the change control with these tasks is executed, the devices are going to reboot, Terminator agent is going to initialize, and devices will start streaming to CVP. If we look at the spline, we can see the banner configuration, and on the leaf 1A, we can see the interface profile configuration. Also, at this time, we can see that MLAG is active, and we have the underlay and overlay BGP neighbors as established. We don't see any VPN routes as of now because the VXLAN interface and MAC and IPVRF configs are still pending. For that, let's jump into day 2 provisioning of our campus network. We have the fabric built, and again piggybacking on the same YAML input file, further configurations like VLANs, port channels, routing, AVP and MAC verbs and IP verbs, etc. can be generated and applied to the container. We have the SV and port channel configlet builders assigned to our top-level container. Let us generate these configurates and push them to the devices. Going back to the devices, now we can see the port channel configuration, the VLANs, the MAC VRFs, interface VXLAN 1, etc. We can also see that we have received and advertised EVPN routes. Here we saw that building the fabric and managing the day-to-day operations like managing software, hardware, configurations, images can be easily automated using the CVP APIs. Furthermore, CloudVision's new Studios application lets users manage device configuration by providing a streamlined workflow that simplifies configuration change operations while ensuring that the network stays in compliance. It gives the ability to make configuration changes in a guided interface without having to edit CLI commands. It comes with out-of-the-box support for common configuration workflows and the ability to create customized configuration workflows. This will be discussed in detail in the follow-on campus webinars. The compliance dashboard provides for security, audit, and patch management. This is 4 sections. Section 1 and 2 show the network device's vulnerability to bugs and security advisories. Section 3 and 4 show configuration and image mismatch. Proactive management of the network is possible with the customized bug scrub available. We can manage risks, avoid issues, and make informed decisions while upgrading. CVP gets a bug alert database from arista.com and checks for bugs based on switch model, EOS version, protocols, and features configured on the device. Days and weeks of bug scrub are reduced and automated. Compliance View is also integrated with the Events page. Events are generated when a device is exposed to a CVE bug. The event lasts until the bug is resolved by installing a hotfix on the device or if the bug is acknowledged. Events page gives visibility into everything important happening on the devices. These events are generated by the analytics engine based on network state along with syslog, and also when certain conditions are met on the predefined interface or device level events, network constraint events, and cloud traceful events, etc. These events can be customized as per the needs of the network or based on the past issues encountered in the network. These generated events can help predict future events like congestion, high CPU utilization, etc. Let's take an example. If in the past we have had a routing table exceed the default 90% route table utilization and caused issues, we could set an alert for a conservative route table utilization, say 70%. This can help proactively mitigate issues before they even happen. These alerts can be sent via email to a Slack channel, WeChat, VictorOps, OpsGenie, and other available platforms. Let's look at metrics dashboards. Dashboards give a flexible and customizable way to monitor the network. Data from different sources can be seen for various devices or interface metrics. The results can be grouped per metric or per device or as an aggregate of metrics for multiple devices. Here is an example of a .1x dashboard which shows 802.1x global status, interface count, and successful endpoint count for all leaf switches. POA dashboard is monitoring the total power approved, total power granted, and total power output by each of the leaf devices. The connected endpoint dashboard shows all the endpoints connected in the network along with their classification, example phones, video conferencing devices, etc. We discussed some aspects of topology view in our last NetBuilders session. Let's talk about some more. The topology view gives a real-time view of the network. Devices are grouped into containers that can be expanded or collapsed or filtered out for a better understanding of the network. Here we can see the devices at the leaf, spline, and spine layers. Topology view provides the ability to monitor health of the network via various link overlay options available. One of them is VXLAN overlay option, which highlights the VXLAN tunnels and the VXLAN tunnel endpoints. The VXLAN link overlay options color code the interswitch links based on which VNI they carry. Filtering based on the VNI is also available, which limits the view to the devices and the links carrying that VNI. To sum up, CloudVision is an advanced network management tool that fulfills all the monitoring and management needs of a modern campus or data center network. Next, I would hand it over to Max, who would discuss some EVPN scenarios.
Thanks, Neha. Hello, everyone. I'm Max Faizi, Systems Engineer with Arista, and I'll take you through this section. Before we actually jump right into the CLI, I will take a minute and review the topology that we're going to use throughout all of our scenarios today. This lab built based on campus layer 3 design with VXLAN and EVPN as an overlay. As mentioned earlier in the call, this design will provide predictable performance and a scaling characteristic as well as the segmentation, which makes it ideal for modern, secure, and scalable campus environment. As you can see on the diagram, interconnection between the switches are layer 3 point-to-point links, eliminating the need for layer 2 loop prevention technologies such as spanning tree or proprietary fabric technologies. The role of campus spline switches in this topology is to serve as a central backbone in which all campus leaf interconnects. Each campus leaf switch has a layer 3 point-to-point link to each campus spline. This simple design, when coupled with the modern operating system EOS and an open standard approaches, provides significant performance and an operational improvement. From a campus leaf design perspective, there are two main configurations which we demonstrate in this lab. Campus leaf 1 as a single home switch and campus leaf 2A and 2B as a dual home leaves. Dual home systems would leverage an MLAC, multi-chassis link aggregation configuration. MLAC is a standard base and is interoperable with any device that supports the LACP. The MLAC configuration supports a requirement for active-active connectivity to address certain applications or devices in a campus environment, such as wireless access points. This is the ability for a workload to survive a single switch failure without impacting endpoint connectivity and ultimately application availability. For the purpose of this exercise, we are using eBGP peering for on-delay and overlay, as well as the iBGP peering between the MLAC peers. The reason for iBGP peering is to cover a specific failure condition that might happen in the campus environment, which I'll delve into further today. In this lab, we're also using VXLAN, an industry standard protocol, as an overlay technology that enables the extension of layer 2 over routed layer 3 fabric. This will be coupled with EVPN, another industry standard protocol, as an address family within BGP to provide a control plane for VXLAN. In addition to point-to-point links, each switch within the topology will have a unique IP address assigned to loopback 0 and will be used for BGP peering within the EVPN address family. All campus leaf switches will also have a loopback 1 interface defined, which will serve as a source for VXLAN tunnels. On the leaf switches in the MLAC domain, the IP address of the loopback 1 will be identical between MLAC peers. This enables the MLAC paired leaf switches to present themselves as a single logical VTEP. Alright, now let's review the first case study. In this case study, we will investigate the broken connectivity between host A in pod 1 and newly provisioned host C in pod 2. The network team had a maintenance window which they provisioned the new VLAN 30 in pod 2. However, the post-check validation failed when they tried to ping from host A to host C. Alright, let us start with our ping test from host A. This is host A, pinging 30, 30, 30, 100, which is host C from host A. And we can see this is not successful. Now let's look at leaf 1. Let's validate the on-delay peering. I'll use show IP BGP summary. And we can see establish peering with both campus splines. We're using the point-to-point links and we are sending and receiving prefixes. All right, let's validate the overlay EVPN peering. We use show BGP EVPN summary, and we can see all switches established, but this time they're employing the loopback 0 IP address for each respective peer and sending and receiving prefixes. Now let's verify VXLAN address table. We use show VXLAN address table. We're not seeing any entry here, which is why host A cannot ping host C. And the same output can be verified from show MAC address table. We're not seeing any VLAN 30 here. All right, so let's jump into leaf to be where the endpoint is connected. Starting to validate our peering for underlay and overlay, I use the same command, show IP BGP summary. And I can see established peering with campus spline switches, as well as the iBGP peering between the MLAG peers established. Right, let's have a look at overlay peering, show BGP EVPN summary. And I can see the overlay peering is also established with campus spline switches. So my overlay peering is fine. Now let's check our VXLAN config. And as a part of the building VXLAN, we are required to configure logical VXLAN 1 interface. Now let's have a look at the output of this command. We can validate that with show interface VXLAN 1. So there was a few outputs that confirms one, VXLAN 1 interface is up and connected. Flood list is dynamically populated via the EVPN control plane. Remote MAC address are LAN via EVPN control plane. And additionally, we are required to map VLANs to VXLAN VNRs that will be used within the VXLAN header to provide the layer 2 service. And this is the under logical interface VXLAN 1. And we can see here VLAN 10 to VLAN 110 and VLAN 30 to VLAN 130. And we can see that there's a shared MAC address between the MLAG peers. All the expected output here. Now let's have a look at the show MAC address table. It seems VLAN 30 is missing here. I'm not seeing any entry here for VLAN 30. Let's check VLAN database, show VLAN brief. This validate if VLAN has been created. It seems VLAN 30 has not been configured on this switch. Let's have a look at the interface, show an interface 5. And we're seeing that has been defined. So it's important to note that just because a VLAN has been mapped to the VNR, it does not automatically create a VLAN on the switch. So let's create this VLAN. All right, let's have a look at VLAN database again. And this time we can see the VLAN 30 has created and it has its member ports. Let's have a look at the MAC address table. And we can see we just learned the 85 MAC address. Right. Okay, now let's jump on leaf 1 and verify the VXLAN address table. Now, there you go. We can see that now this time we got VLAN 30, we learned the MAC address through EVPN. It's behind VXLAN 1, behind the VTEP 22234. And we should see the identical output under the MAC address table. Yep, we learned dynamically through VXLAN 1. And there you go. Here are our ping results on host A to host C. So in the conclusion, it is recommended to keep VLAN creation and VLAN to VNI mapping consistent across all VTEPs with all required EVPN configuration. And one way to ensure the consistency of the configuration as well as the ease of ongoing operation is to leverage CloudVision Portal CVP as an automation turnkey solution for initial and ongoing provisioning. Okay, let's go ahead and cover the second case study. Failure on campus spline facing links and see how the network will react to this event. In this case study, the networking team had received event notification on CVP indicating BGP peer down on campus leave to be. Now we want to investigate if host A can still reach to the host B and how the network converges from layer 3 control plane and forwarding perspective. Right now, between the two campus leaf peers, leaf 2A and 2B, we have the MLAG peer link, port channel 1000, which is used to synchronize the layer 2 control plane between two peers. And we also have VLAN 4093 and the SVI associated with this VLAN for IBGP peering between the MLAG peer for layer 3 control plane. All right, now let's go ahead and validate the underlay and overlay peering on both MLAG peers. Let's start with leaf 2A. I will use show IP BGP summary. And we can see the established peering with both campus spline switches. We can see that they're exchanging prefixes as well as IBGP peering with campus leaf 2B. Now let's review the overlay peering. And we can also see the peering is established for both campus splines from leaf 2A. All right, so let's jump to campus leaf 2B. I'll run the same command to validate the underlay peering. And we can see the underlay peering between leaf 2B and campus splines are in idle state. However, the IBGP peering with leaf 2A is still established. All right, now let's have a look at the interfaces. And we can see that both Ethernet 2 and 3 are down. Those are the northbound uplinks between campus leaf 2B and campus splines. And we can also validate the VLAN 4093 SVI, which we use for IBGP peering between the MLAG peers. Now it's interesting to see how the overlay looks like. All right, now we can see that both peering between the campus leaf 2B and splines in the overlay are intact and established. And this is despite the uplink being down, showing that network has converged and it's maintained its EVP and peering station with the splines. Now let's have a quick look at the MLAG status. And we can validate the MLAG is up and running, and the peer link is port channel 1000. Let's have a quick look at port channel 1000. And there you go. We can see that Ethernet 1 is in use for peer link and it's up and running. All right, let's jump to host A to validate the reachability. Let me stop this ping and start again with the destination 10.10.10.200, which is host B, and this is from host A. And we can see the pings are transmitted successfully. All right, now given the host B is attached with MLAG, there is a chance that ICMP replies lands on campus leaf 2A or 2B. In the case of packets arrives in leaf 2B, the switch will perform the VXLAN encapsulation and then forward it through leaf 2A via the peer link and then over to leaf 1. Okay, let's have a look at campus leaf 1. I use show VXLAN address table. And we can see that we land the remote VLAN 10 MAC address via EVPN behind the VTEP 22234. And we should see the same output within the MAC address table. Okay, now to wrap up. We have seen the uplinks on campus leaf 2B were down, hence causing the underlay BGP peering tier down. But despite the failure, we had the pings going across the host. And the only reason that works is one, it still has the EVPN peering with the spline. So it still has the necessary control plane state to make this decision. And two, once the decision is made to forward to leaf 1, it has the reachability to loop back 1 on leaf 1 because of that peering between leaf 2A and leaf 2B in the underlay. And that's how this campus leaf design provides network level resiliency to the endpoints. Thanks for your time. Over to you, Paul.
That brings us to the end of the webinar. We hope that you found the topics useful, and we thank you for your participation with questions throughout. Keep an eye out for new webinars within the NetBuilders series being published on the arista.com website. We look forward to seeing you next time, and in the meantime, please reach out to your local Arista account team for further information. Thank you and enjoy the rest of your day.